Hi everyone, today we're going to keep working on what we've been doing with finding volumes by revolution, but these problems are going to be a little bit different. So if you remember the first group of problems we did, when we revolved our curve around the x-axis, it made a solid and all the cross sections, if we could slice it, were circles. So we called that our disk method. But now what we're doing is we called the washer method, and here's why. Sometimes we're trying to find the volume of a solid that has a hole in the middle. So if you can envision this solid, right, if we wanted to find this volume, we would need to subtract out the volume of that hole. So when we have a solid with a hole in the middle, we still use, I'm going to say we're going to still use areas of circles to find the volume, but we will need to take away the volume of that hole from the overall volume. And so to do this, we're going to be setting up two different integrals to start. Now, keep in mind, this can be with respect to x or to y. And so I'm going to represent it with x here, but it could be either. And so here's what we're going to do. We're still going to be using integral to add up all the areas of those circles. So we're going to have pi times the integral. I'm just going to say the interval from a to b. Now we're going to have a big R squared dx. So that's going to be kind of like the whole volume without the hole. But then we're going to subtract out the volume of that hole, and so we're going to have another radius that we're going to call little r. Now the idea here, big R is what we're going to call our outer radius, and when we do some problems we'll really look at what this means, and then little r is going to be that inner radius. And again, really this second integral that we're subtracting, that's just accounting for the volume of that hole that we want to take away. Now, one thing that I want to make a note of, and so I'm going to make an arrow down here. Since I have two integrals, they both have a pi out front and they're both over the same interval, you'll see a lot of times I'm going to condense this into one integral. So it's going to be pi times the integral from a to b. Now I'm just going to take my big R squared and I'm going to subtract my little r squared. Notice each of the radii are squared individually, and then I have dx. So that's what a lot of this work is going to look like. So let's look at some actual problems now and make sure we know how this all comes together. So for number 1, we're going to do the setup all without a calculator, but then we'll use our calculator to actually find the value of the integral. So we're finding the volume of the solid of revolution formed by rotating the region bounded by these two curves, and we're going to rotate it about the x-axis. So let's see what this is going to look like. I'm going to try to spread this out here. Alright, so let's see, y equals square root of x minus 1. So this is going to be our graph of the square root of x, but it's just going to be shifted over to the right one. So it's going to look like this. Let's see, 0, if I plugged in 2, that would be at 1. So it's going to curve up like that. Now if I do x minus 1 quantity squared, again that's my parabola, y equals x squared, but also shifted to the right one. So that's going to look like this. So now what I'm doing is I'm rotating the region bounded by those two curves. So I'm rotating that region about the x-axis. So there's a couple things I want to note here. So here's my region. Since I'm rotating it about the x, I'm going to draw in my kind of slices that way. And I'm going to highlight, just like I did before, I'm going to highlight that axis that I'm revolving about. And what you're going to notice in these types of problems is between the region that I'm revolving and the axis that I'm revolving around, there's a space in here. And that's what creates that hole. If we think about like we did before, kind of sketching the reflection here, I'm going to have almost like a bowl when I revolve this. It's going to have a hole in the middle. And so that's why we have to account for subtracting out that volume. So let's take a look. We still know our cross sections are going to be circular. They're just going to have holes in them, so that's why we call them washers. So we're still using our pi r squared. Since we're revolving about the x-axis, we're still going to have r equals top minus bottom. But now I need to identify a big R, let me pull down here, our outer radius, and the little r, which is our inner radius. So for my big R, that's going to go from the very top function, so here, all the way down to the axis, so down to here. That's my big R, and I know that's hard to see. So my big R is going to be the top curve. Well, that was the square root of x minus 1. The bottom is the x-axis, so it's minus 0. So my big R is the square root of x minus 1. Now, my little r is what accounts for that kind of blank space. So it goes from here down to my axis. The little r is that inner radius that fills in the blank space. So the top of my kind of blank space here is my curve x minus 1 quantity squared. The bottom is still the x-axis, so minus 0. So my little r is x minus 1 quantity squared. So now that I've got my big R and my little r, I can just plug this all into my integral. So I'm going to have pi, right? That comes from my area formula. My interval, I'm integrating between 1 and 2. I'm using those x coordinates. Now I'm going to have a big R squared. Right? This is going to be my big R squared, and I'm going to subtract out a little r squared. I should have kept this consistent. This should be my big R. This would be my little r squared, and then I would finish that off with my dx. So now my big R here was square root of x minus 1. I'm squaring that because we have r squared. My little r was x minus 1 quantity squared, and again we have to square that. So now we're going to type this all into our calculator, being really careful to account for our parentheses. So let's see, whoops, hopefully this doesn't die on me. So I've got pi math 9 integral from 1 to 2. I'm going to have square root of x minus 1. I'm going to square that, my big R squared. I'm going to subtract out my little r squared. And I've still got to square that. So x minus 1 squared was my little r. I still need to square it. And then if I hit dx, my answer is about 0.942. So that would be the volume of that solid with the hole in the middle. Again, the way you're going to identify these solids that have holes in them is anytime you have a gap between the region you're revolving, so blank space between that region and the axis that you're revolving about. All right, let's look at another one. So let's see, for number 2, we're going to find the volume of the solid of revolution formed by rotating the region bounded by the graphs of y equals root x and y equals x cubed, this time about the y-axis. So I'm going to try to make this bigger so it's a little easier to see what these regions are. So y equals square root of x, I know is going to look like this. And then y equals x cubed, I know is going to come up this way. And then it's going to go like this. So those are my 2 curves. Scooch this over. And let's see, now I'm revolving about the y-axis. So I like to highlight this here. So if I'm revolving about the y-axis, I know I'm going to integrate with respect to y. And again, I can see in between this region that I'm revolving and the axis, there's all this blank space, and that's what's going to create my hole and the need for the little r. So again, our formula is a equals pi r squared. Now this time our r, because we're about the y-axis, is right minus left. So my right bound is y equals x cubed, but since we're with respect to y, I need to solve that for x. I'm going to do that by taking the cube root of y. So x equals the cube root of y. And I'm going to need to do that for my other as well. Y equals the square root of x is going to give me x equals y squared. So now my big R is going to go from the axis all the way to the rightmost boundary here. So for this is my y equals x cubed. So instead, I know that's the cube root of y. Minus, this is x equals 0, so it's minus 0. So my big R is cube root of y. Remember, my little r is what fills in that blank space. So now for my big R, it's always right minus left. My right now is my square root of x, which we know is actually y squared. And again, my left is x equals 0. So my little r is y squared. So we've got our big R and our little r. So now we're ready to set up our integral. So our volume is pi times the integral. Now remember, we have to use y values here. So this is going to be from 0 to 1. And I'm going to make a note that these are y values. So now I'm going to have my big R squared. This would be big R squared. Minus my little r squared. And then I would have dy. So my big R is cube root of y. My little r is y squared. And now I've got an integral that I can plug into my calculator. So let's take a look. Whoops. It's getting mad at me here. Math 9 from 0 to 1. I've got x to the 1/3 squared minus x squared squared, whoops, and then dx. And I get approximately 1.257. All right, we're going to do one more. We're only going to do part A of the next one, but I want you to see, so far we've just been revolving about the x or y axis, but we can actually revolve these curves about any horizontal or vertical line. So that's what we're going to look at now, and then we'll leave ourselves one to go over in class. So let's look at part A. So now we're finding the volume of the solid generated by revolving the region bounded by y equals square root of x and the lines y equals 2 and x equals 0, and we're going to revolve it about these other lines. So first of all, let's look at what we're doing here. Y equals square root of x so 1 2. So I've got my curve y equals the square root of x. Let's see, it's bounded by y equals square root of x, the line y equals 2, and x equals 0. So it looks like it's this region in here that's trapped here. Now we're revolving that about the line y equals -2. So I'm going to draw that in green. That's my axis there. Now here's what we have to think about. Since the line y equals -2 is parallel to the x-axis, I'm going to make a note here that we're integrating with respect to x. Because again, that line y equals -2 is parallel to our x-axis. So the region we're revolving is this one here. And obviously we can see we have a huge space here between the region that's being revolved and our axis of revolution. So obviously here we're going to have a hole in the middle, so that means we need two different r's. Now, in this case, we're integrating with respect to x, so my r is still top minus bottom. So let's take a look. My big R is going to go all the way from the top, all the way down to that axis of revolution. So my top, well, that was the line y equals 2, minus my bottom is the line negative 2. So I'm doing 2 minus a negative 2. So my big R is a positive 4. Now my little r is what accounts for all this blank space. Still top minus bottom. So the top of my little r is our function y equals square root of x. My bottom is still negative 2. So my big R now is square root of x plus 2. So now when we set up our integrals, let's see, we were still with respect to x. So my x values are from 0 to 4. I still have my big R squared. I'm subtracting my little r squared. That's my little r. And we're going with dx here. So my big R was just 4. My little r is square root of x plus 2. And now we're going to type this in. So let's see what we get here. I know. Okay. Pi from 0 to 4 of 4 squared minus square root of x plus 2 quantity squared, and then dx. And I get 58.643. All right, so I'm guessing at this point that we've generated some questions, so we will save part B for class so we can go through that all together, and then you'll spend a good chunk of time just practicing this and making sure we can recognize when these solids are going to have holes in them. All right, see you when you're back in class.